Hello and welcome. My name is Maxim Naumov. I'm a research scientist at Facebook, and I will have a pleasure to talk to you about deep learning recommendation workloads with implications on hardware and system platforms. This will be a joint talk with my colleague Divatsa, and we also would like to thank Whitney for helping put the slides together. First of all, let us delineate the difference between deep learning and artificial intelligence. Artificial intelligence is a large field which studies programs with ability to learn and reason like humans. Machine learning is a subfield of artificial intelligence which studies a set of statistical techniques that allow machines to improve with experience. And deep learning is a subfield of machine learning that uses multi-layer neural networks which adapt and learn from vast amount of data. Due to deep learning success, many people equate machine learning and AI, but these are actually different, as we have shown on this slide. Deep learning is unique. If we plot deep learning methods versus other methods, standard machine learning methods, on a plot where we have accuracy on the y-axis and data size and model complexity on the x-axis, we'll see that as we have few data points and we have relatively simple model in terms of number of parameters, other methods will outperform deep learning methods. But as the amount of data and model complexity increases, deep learning methods often outperform their counterparts. Let us take a more concrete example. Let's take an ImageNet data challenge and use a ResNext 101 model with group convolutions. We will see that if we increase the number of parameters in our model by doing different convolutions, starting from 32 by 4D and going to 32 by 48D, an increase of 20x in number of parameters, we will see on the right plot that the gray curve goes up. So as we increase the model size, our accuracy improves. On the other hand, if we take a different data set for training, we take a data set of Instagram images, which is about 65 times larger, train the same model on it, and then perform inference on ImageNet dataset, we will see that the model will follow the purple line. So by using more data to train, we'll improve model performance, and it will continue to improve as the model becomes larger and larger. Let us now talk about machine learning growth and scale at Facebook. On this slide, you are seeing a typical pipeline used by machine and deep learning models. We start with data, extract some features, construct and train a deep learning model. We perform evaluation, perhaps improve the model and the features, and eventually deploy the model. Let us now focus on different growth of different parts of this pipeline. We will see that in terms of data, about 30% of data was used for machine learning pipelines in 2018. Today, it's about 50% of the data, and also the amount of data has increased. So this leads to a growth of over 3x in 1 year. Also, more than twice the number of ranking engineers are working on deep learning and machine learning models, and they are running more than 3 times the number of workflows. Further, the compute consumed by these workflows has also increased by 3x. And finally, we wanted to point out that we perform a large number of predictions by the models that are deployed after training. For example, per day we perform 400 trillion predictions, 6.5 billion translations, and also these models allow us to remove more than 99% of fake accounts automatically. This pipeline exercises many of the infrastructure components, and it has many challenges. Data and features rely on storage, training, evaluation, and deployment for inference rely on compute and memory. And also training can rely on network. And all of these components need to work together. In order for all of these components to work together, we require that the models and the system design are co-designed together, and they require hardware and software co-design. Co-design refers to the concurrent design of optimization of several aspects of the system, including hardware and software. And the goal of co-design is to achieve a certain target metric, such as throughput, latency, or power. We often start with system with specific requirements and workloads. We design our chip or a system architecture. We develop software and hardware in parallel and deploy them together, iterating until we are successful. Now that we know that we need to specify the workloads at hand, what are the workloads that are important for us at Facebook? Well, we have three main vectors: ranking and recommendation, which is used in newsfeed and search; computer vision, which is used for image classification, object detection, and video understanding; and language, which is used in translation, speech recognition, and content understanding. These models used in these frameworks use different types of operators, but what is important to know is that only 40% of time is spent in dense matrix multiplication in FB production models. This figure is also deceiving because part of it is consumed by convolutions that have been resized and reshaped into gems, and the gems corresponding to convolutions are not of square size. So this further diminishes the amount of time spent in square matrix multiplies. We also notice from this figure that embedding lookups play a significant role in the operators that are used, and that tensor reshapes and other ops result in a long tail of operators that run in the data center. We can also look at the relative importance of the models. We see that compared to language, computer vision models require 10x the relative capacity, and ranking recommendation models require 100x of capacity. This might come to a surprise to many of you because many people outside of the data center focus on language and computer vision models, but recommendation models are actually among the most important models that run in the data center. They also have very different characteristics. If we plot computer vision and natural language processing models on a plot where we put arithmetic intensity on the y-axis and model size on the x-axis, we will see that computer vision models, often expressed through convolutional neural networks, have very high intensity and relatively small model size. On the other hand, deep learning recommendation models, DLRMs for short, are huge. They have very large embeddings and require a large memory capacity to store them, but they have relatively low arithmetic intensity. So let's look at a concrete example of a deep learning recommendation model. This is a model that helps us choose a small set of items out of many. Its input consists of dense and sparse features. We'll come back to explain what these are in the next slides. Dense features are fed into bottom MLP layers. Sparse features are fed to embedding tables, where embedding lookup is performed. The features are interacted, and the results are fed into the top neural network, which often consists of MLPs. We have wanted to point out that we have open sourced this model at Facebook Research GitHub website under DLRM, and you can see the definition and the code for it there. Let us look at different components of this model and what they are in practice. Different features, dense and sparse features, simply correspond to floating point and integer numbers, and they exercise storage. They're stored. Embedding lookups can be seen as sparse times dense matrix multiplications, and they exercise memory bandwidth. On the other hand, if we are doing distributed training, and Divatsa is going to talk more about you in the coming slides, interconnect will be exercised by all reduce and potentially all-to-all operations. And finally, top and bottom NN exercise compute and can be seen as dense matrix multiplications. What is the relative size and requirements of all of these different layers in this model? Well, the features themselves require about on the order of 10 petabytes of storage, necessitating a centralized data store and ingestion over network. MLPs used in the top and bottom neural networks eventually require gem operations which exercise compute on the order of 10 teraflops. Finally, embedding lookups require two things from the memory system. They require memory capacity on the order of hundreds of gigabytes with multiple embedding tables, each taking several gigabytes. And they require memory bandwidth of up to 1 terabyte per second, which is exercised by the multi-hot lookups into the embedding tables. And finally, in distributed training, if we use synchronous training with model and data parallelism, all reduce would be used for data parallel MLPs, and it is bandwidth intensive with messages of up to 10 megabytes. And all-to-all would be used for embeddings, and it is latency and bandwidth sensitive with messages of 0.1 megabytes in size. And now, my colleague Divatsa will proceed to tell you more about the training of DLRMs and the trade-offs of that.
Thank you, Maxim. Hi, I'm Divatsa. So just to pick it up from where Maxim left, just a brief recap. So DLRMs, or deep learning recommendation models, are a very important class of models for us and in industry. And these are not like common deep learning workloads. The key differences are these have very large model sizes, typically up to hundreds of gigabytes, and trained through petabytes of data. Both of these characteristics essentially necessitate that the training of such models is done in a distributed fashion. To be able to process that much of input data in reasonable time and have a reasonable throughput, and additionally be able to accommodate these models. Given the size of the model poses another unique challenge. Typically, if you look at common distributed training for other deep learning applications such as computer vision or neural machine translation, they are parallelized across the mini batch size, which is data parallelism, and the weights are replicated and independently processed, and in the backward pass, the gradients are accumulated and applied. That doesn't necessarily work for DLRMs, because replicating hundreds of gigabytes of the model across all nodes becomes prohibitively expensive. So the other type of parallelism, which is essentially the model has to be distributed, or model parallelism, is an essential requirement for the distributed training of DLRMs. But as recapped previously, the DLRMs also have the MLP component, which are typical fully connected layers. These are much smaller parameters, and these can be replicated, and it's preferred to replicate these to be able to have faster throughput. So we need a combination of data and model parallelism. So it has very unique or uncharacteristic requirements for distributed training. Additionally, the distributed training itself can be implemented using multiple strategies. One of the more popular approaches for such models is the parameter server based master worker model, which essentially tries to disaggregate the setup, have a combination of trainers which are processing the MLPs, are data parallel, and then another set of parameter servers which essentially hold the model and can be scaled independently. Both these, depending on the requirements, can be scaled independently and provides a very good value proposition. However, the communication between them becomes a bottleneck. The other more common approach is to essentially use a completely distributed approach, have every node work as a worker, processing different components of the model, and then using collective communication to synchronize between them. Here, I'd like to also point out, we have a recent paper that we posted on arXiv, which talks about the various details and the different types of and the considerations of deep learning training in Facebook data centers. So as a snapshot, if you look, if you were to summarize, this is how the training of DLRM looks like. So we had the schematic of what DLRM model. Now, if you can look at each component, the embedding lookups are model parallel, they're memory intensive. The MLPs are essentially compute intensive and are treated in a data parallel way. Then you have the feature interaction, which both of these interface, where there is a transition from going from model parallel to data parallel. All of this looks very clear or can be easily demarcated on paper, but the detail or the complexity is when we actually try to look at under the hood and how it pans out when it's actually implemented on a hardware or a training platform. So if we map that very nice demarcation of model parallel on embeddings, data parallel MLPs, it maps to something like the picture on the right side. So you have you have few nodes P0 to P3. This is one candidate configuration processing the embeddings, and then you have the other nodes P4 to P7 processing the MLPs. The MLPs are happening, as you can see, replicated on each of these nodes, and there's a reduction happening across them, which has to be orchestrated and overlapped with the compute so that the communication does not get exposed. While at the same time, the nodes processing the embeddings need to be able to have an all-to-all communication to take their partial outputs or the lookups from their local embeddings and communicate them all to the sub batches to the other nodes. So this becomes a fairly complex application or an articulation of the training model. So when we look at any training framework or the platform used for expressing this training, it needs to have a lot of flexibility and features. Here we're going to talk about how PyTorch gives us gives us benefits and allows us to very effectively express a complex model like DLRM and its distributed training. Here are a few key tenets of PyTorch itself. So one of the key basic principle of PyTorch has been the eager and graph-based execution, which allows for fast experimentation and support dynamic neural networks. Although these are not mainstay requirements for deployed application, it provides a very nice feature to be able to experiment in very quickly prototype models. The key things which actually help DLRM or which we used to which we've showcased in the PyTorch DLRM example is the distributed training support in PyTorch and the support for different hardware backends such as the NVIDIA GPUs, which are more common. Additional to them, the same abstraction works with AMD GPUs and other additional accelerators through backends such as Globe. And overall, simplicity is preferred over complexity. And as you can see in the next slide, where we actually talk about how DLRM or a complex model like DLRM, which we talked in the previous slides, can be very simple, expressed in a few hundred lines of code. Again, I invite all of you to go back to GitHub and look at the code itself. Here are a few snippets. And if you look at the model implementation, one thing that would stand out is it's been implemented very similar to the illustration that we had before. To make it more intuitive, the MLPs are separated out of separate modules. There is the embedding, and these things are connected with the simple graph or the schematic that we had before. And depending on what configuration you want to run, this can be specified through a few simple command line arguments. Now, going back to the requirements of the system or platform implications, if you look at the application DLRM, given that it's a very important class of, or arguably one of the most important class of applications for companies like Facebook or other large hyperscalers, if you look at its requirements, it requires tens of teraflops of compute, not hundreds or more like the current accelerators. However, it also requires terabytes of memory capacity to be able to store large models and train with them, and memory bandwidths of terabytes per second. And additionally, given that everything has to be distributed, interconnect bandwidth needs to be in hundreds of gigabytes. So if you look at current systems that are available today, the CPUs, which are ubiquitously available in data centers, provide everything and provide only the memory capacity, but lack on everywhere else. And then the alternative is the accelerators, which provide a lot of compute, which is not necessarily beneficial in DLRMs, but they have bandwidth and interconnect. So if we look at how we want to arrive at, or how we want to approach building a system or a platform for such application, it's best to consider things in terms of ratios and balancing the system out for such an application. Here I'm going to use DLRM as a class of or representing a class of applications, and it's good to look at memory. So having a lot of compute, hundreds of teraflops, with not the backing memory would cause bottlenecks. Similarly, having memory capacity without the bandwidth is going to make things unusable. And just like we look at the flop to memory ratio, the same thing, additionally, we should also look at the flops to network, given everything that happens here has to be distributed. So again, you have a lot of flops, then there should be appropriate or sufficient network bandwidth to be able to use these flops in a distributed environment and not be limited. So just to summarize, if I were to say an ideal system platform, what it would look like for this class of application, tens of teraflops with variety of precision, given the precision requirements here are also atypical, terabytes of memory capacity with terabytes of bandwidth, and also fast interconnect, hundreds of gigabytes of bandwidth, and importantly, flexible topologies allowing easy architecting systems which can be easily deployed in data centers. So stepping back, if we were to summarize all of this into call of action for this community here, we want to kind of reiterate that deep learning is beyond regular computation or regular dense gems. There is increased focus on memory subsystems, capacity and bandwidth also, and these are very important class of applications which are used in widely across companies. And anything which at a practical scale, when we look at training, it has to be distributed. So optimizing for a single throughput on a single machine is not advisable or not useful. Instead, looking at a holistic system approach makes it a lot more sustainable. And since everything needs to be distributed, faster interconnect and having flexibility is very important. To learn more about this DLRM or this class of application, again, here is the link to the DLRM code on GitHub. Additionally, this is to work. I mean, Maxim has been working on this over the last couple of months actively to ensure to add DLRM as part of the standard benchmark suite of MLPerf. So it's part of MLPerf training benchmark at 0.7. Additionally, if you look at anything that we do at Facebook, the systems are designed in an open way. We contribute back to the OCP community, and systems we design for training Zion or anything further will be contributed back. And we again invite you to look at the OAM or the OAI specs, which are basic building blocks for our systems. Thank you.
To change over to Q&A.